democratize AI. So let's learn all about it. Thank you.
Thank you. All right. So I chose this title very deliberately because AI is causing a lot of friction at the boundaries of people with and without resources or access to technology or people who know how to use it. And I strongly feel if it's not egalitarian, it's going to be harder for us to be successful in this venture. So that's one part. The other is if you yourself don't get involved in building something with it, it's always going to be that black box that you'll never trust. And till you don't build your own little black box, or let's not call it a black box, but your own box that you can tweak and play with, you are now going to be able to guide that technology to include what you feel is important. And so it's really critical for all of us to take part in this. So let me get started. So first I'll talk about my journey into this, but I'm also going to then give you why I dislike the word AI and how do you sort of start liking it a little bit and then doing more with it. I'll take you through some AI index and hype cycles and how you can sort of figure out where you should be paying attention and where you should be ignoring things. And then you heard this morning from the talk about imageomics, the foundation models are central to a lot of what is happening and how do you use them for what you need to do. And then the key part is adaptation of those models to your work. And there are many places where you can do that. And then I'm going to try something which might blow up in our face, but I'm still going to try it, which is I want you to try and build a model along with me or train something. Show of hands, how many of you here have taken something and trained a model and then done some inference on it? Show of hands. Okay, few. How many wish you could do it? There's a whole section that's not raising hands at all. And I'm hoping that you will participate in it. So if you have a laptop, please join in. It will take about 5 or 7 minutes, and I hope it works well. And then the last part, which is going to be the bigger section, which is building the AI community of practice. Again, I very strongly feel if you don't have a community of practice, you're just going to get traveling salesmen who come by, pitch something to you. You may or may not jump into it. And if you jump into it, you may have remorse when that salesman is no longer visible. And so you have to be in charge of your destiny. And the only way you can do that is if it's a community, not an individual. So, and you guys are already a community, but there has to be an AI community of practice as well. And then the image there is the magic of the unicorn, because everybody expects people who can come and do things with AI as the unicorns. And I think everybody can be a unicorn. But the good part about this book, how many of you know Choose Your Own Adventure books? Yeah, right. And so anything in AI is also choose your own adventure, because you can go different routes, open a random page, then go back to the prior page and then weave your own story. And that's what I'm going to talk to you about today. So first, I would definitely have to thank the Stover Center for being an amazing host and the hospitality, and more importantly, Sophia and the organizing committee that invited me. I really enjoyed my time here. And I also want to thank my team at the University of Arizona, at the Data Science Institute and Cyverse, and our AI Institute at Iowa State, University of Arizona, and Carnegie Mellon, whose work I'll be talking about. And I've been to Kansas City before. I would say this is the best weather I've ever had. So thank you for ordering that. And looking at the trees and the redwoods, I am in heaven right now. So thank you. So my own journey, I sort of came from India in the early 90s. I was a systems engineer by training. I wanted to marry that with the love of biology and automation, and then take things from systems engineering and apply it to biology. And most programs didn't want to talk to me because they thought I was strange and interdisciplinary engineering was non-existent. So I had to go into a very traditional systems engineering department and then convince my advisor at that point that robots are also important in biology, or optimization will be needed there as well. I was fortunate that I found one. He didn't get his tenure, but I was not the reason. And that brought me to Tucson, Arizona, which is a very beautiful place. Hiking around Tucson is fun. It also is a city of gastronomy, the first one in the US. So that's good food, good weather, and most of the time except for the summer. But otherwise, an awesome place to be, where I've been here 30 plus years. I do tell the students that I've watched the saguaro cactuses grow on campus and even get arms. So it's been a long time. So this is my campus. Again, it's a lot of fun. The good part is you have the optics, you have the engineering, and the culture is so collaborative that you can walk into a department and pitch an idea, and you get 3 other people who will write a proposal with you. So I've loved to be there, and my work spans everything from astronomy to zoology. I couldn't expect a better place to be. So what do I do there? This sort of describes my life in a way where I try to reduce the friction at the boundaries of emerging computational methods and technologies as they get applied to domain sciences. And my team sort of works at taking these technologies and making them more usable, more scalable. But we are like that sandpaper that's trying to make sure that people don't get hurt when they cross between those boundaries. And at the same time, they are productive in what they do. And for some of them, it also allows them to find their needle in the haystack that they're after. And often we teach them how to move those large haystacks to different parts that will allow them to find that needle. Lately, that's been moving data to GPUs. And so we spend a lot of time building tooling that usually nobody sees, but everybody needs. And I'll give you some examples. So my journey sort of more in this space began in 2004, 2006. It's almost been 20 plus years. Some of you here have known me through the days of iPlant and then Cybers. So in 2006, NSF put out a call. They wanted the plant scientists to think differently about computational at scale. So we were born. One of the key things was we said we will not reinvent the wheel. We'll go to different disciplines and borrow ideas from them, and then develop middleware to connect those. And that's what we did. Took us a while. 2010 is when we started building things. The community started using it, and our mission became design, deploy, and expand national cyber infrastructure for life sciences research. And most importantly, train scientists in its use, because NSF was pouring money into the computational information sciences, but the biologists were not touching it. The only people, well, the protein guys would jump and consume the cycles, but everybody else was not able to use it. And so we had to change that landscape. And so 2013, our focus sort of became more broader. And by 2016, we had the astronomers, the hydrologists, everybody using the same infrastructure, because it was like Lego blocks. You could connect what you wanted and you did what you needed. And so we became sort of transforming, data-driven discovery was where we went. 2025, now we have federated places. People use the same infrastructure. It's also in commercial entities, Fortune 100 companies. They take things, they license it from us. And then we also started getting more and more into the AI institutes that we were part of. There were synthesis centers. We had crossed over 125,000 users, many petabytes of data. And the emphasis on AI ML was becoming rather large. And so that opened our eyes to what is missing in that space. And the little cactus that you see right there, that is, I'll talk about that project called Verde. That is our friendly LLM. And so before I go down that path, I do want to remind people of the Clarke's third law, which is any sufficient advanced technology is indistinguishable from magic. So right now, a lot of what we equate to AI is approaching that magic, and you're like, wow, how did that happen? And it's going to happen for a while, but it's not the first time that this has happened. We have gone wow on technology and treated it like magic. So my sort of distaste for AI, I prefer to see it as augmented intelligence rather than artificial intelligence. And the main reason for me is that there's too much marketing hype, and I'm old enough to remember parts of the AI winter. How many of you know what AI winter was? Okay, yeah, I can see some gray hairs and some not so gray hairs raise their hand. But things were oversold, and then, you know, things didn't pan out. Obviously, the technology landscape was different. The amount of money being poured was different. Now it's very different. But people expect way too much the moment you say AI. They don't want basic things. They want it to be doing something magic. When you say machine learning, they look at you and they feel like, yeah, you're so old school. Who does machine learning? Then you have to explain that that's what's fueling this. And I think Ido and I were discussing this, and I've sort of thrown in the towel and I said, okay, call it AI, but in my head, it's augmented intelligence. It's not artificial intelligence. And so if we design machines to complement what we do rather than replace, it's a better way, and we can customize it to what we need. And even though the industry is gunning for AGI and they want the AI to do everything, we know that's a goal far away, but there are so many small victories that are to be had that you can adopt to do important things. I don't have to convince anybody in this room, but if you do go to PubMed and put in those words, you can see, 50, 60, 70, 80,000 papers a year that are around this topic. It's not humanly possible to keep up with it. And so you have to decide sort of what parts make sense for you and how you're going to use them. How many of you have seen the Gartner hype cycle? Okay, few of you. Those of you who haven't, Gartner being the company that does a lot of work in consulting, and they make a living by advising everything from academic institutions to large companies on their strategy on managing technology. So on the top right, what you see is symbols that explain to you, how many years will it take to reach a stable state. So what you see at the bottom is the innovation trigger. A technology is born. After a while, it goes into the peak of inflated expectations. People expect more from that magic, okay? And then they realize that magic is not as much as what they thought it would be. So it's followed by a trough of disillusionment where they say it sucks, and it's nice to see cloud AI services in that suck region. And then it follows the slope of enlightenment where you start saying, oh, you know what? I can do something with this. And it's good to see knowledge graphs and intelligent applications there. And the plateau of productivity is when all of us are starting to use it and we don't talk about it. It's just there, but it's productive for us. And so that's computer vision, which says in less than 2 years. And you guys can see how some of these systems that are doing vision are there. So it's worthwhile to go every year and see where the technology is on this hype cycle and how many years are there, so that when somebody tells you, I can do this magic, you can go back and say, nah, come back after 5 years, we'll talk. The other thing I like to read is the Artificial Intelligence Index report that comes out of Stanford. It's absolute no nonsense, and it is at a global scale. And again, it gives you very good understanding of where things are headed. And 2025 is supposed to literally come out this week, but it hasn't. So I'm going to still give you the 2024. How many of you read this AI index? If you haven't, please do. It's completely worth it. And what I love is all that data is on GitHub. You want to reanalyze that, go for it. And that's, to me, that's an important way to convey these things. And it's not, there's no hype, it's straight to the point. So they started talking about, robust and standardized evaluation of LLM responsibly are lacking. And you can see that each industry and each provider is doing their own thing and then coming up with benchmarks. And so it really complicates things. So that was number 5 on their top 10. Number 6 was generative AI investment is skyrocketing. You're starting to see $25 billion. I know, given what's happening to the market, doesn't sound like a big number, but it's a huge number. And for us as academicians, it's important to know where that is going, because then you can take in the issues of segment anything is coming out from, or Llama 4 came out just, 2-3 days ago. Can I use it? And it's important to keep an eye on that if the investment is happening, because the foundation models allow you to do things downstream. And then the AI makes workers more productive and leads to higher quality work. I know we can question that, but in reality, that is what the analysis is showing. But the last part was really important, which is AI is the potential bridge to the skill gap. As many of us retire and disappear, we take a lot of our knowledge with us. How do we encapsulate that and preserve it for improving things where we would be the handful of people that have seen that and not have a chance for everybody to see it. So it's important for the gaps that have to be filled. But then the last part is without proper oversight, it leads to diminished performance. Remember what I said, AI, when you start trying to say, I'm going to replace this completely, a human being very rarely, especially in academia, is not just doing one thing, they're doing 15 things. And if you say, I'll reduce your workload by 3% or 5%, we don't have 100,000 workers in the same organization doing that, where we say, let's remove these people and give them a higher order task. We're already all working at 130%, and reducing 3% doesn't really change the calculus. And so bringing in those things that are efficiency based, that don't involve the human being itself, doesn't scale in academia. So that's sort of the important part where it'll diminish the performance. And the number 8, which I just wanted to put there because science progress accelerates as people start using more AI. So no surprises there either. So what is a foundation model? You heard this morning. How many of you know what a foundation model is? Some of you, right? Good. Now, those of you who don't, I highly recommend, again, the same group from Stanford HAI has this what is a foundation model, and I'll talk a little bit about it. But literally every innovation, whether it's LLMs or segmenting of images or labeling of images, at the bottom of it is a foundation model that is driving what you can do as the next step. So what does the foundation, how does the foundation model become useful for us? Again, this is from this paper. Actually, I shouldn't call it a paper. It's more like an encyclopedia, but this is on the opportunities and risk of foundation models. It's from 2022, but it's the who in the AI space, but very discipline specific, have written where they see the opportunities and where they see the challenges. So it's 110 authors, but it's very nicely put together. And if you are curious about it, read this rather than some random blog. It'll be really an interesting piece. So this figure is from there, and you sort of see the data creation. Also, there is data curation. So machine learning people really care about it, or at least the ones that care about their data and output care deeply about it. But the adaptation, taking a foundation model and making it useful for a given discipline, whether it's segmenting or imaging or counting, and then the deployment happens. All of you need to be part. Obviously, the curation is there, but the adaptation, and it's a cycle. If you are not changing that to tuning that to your task, often you are setting yourself up for substandard performance from those models. The biggest threat I had seen about 2 years ago, which really had scared me, what you see in this figure is how many models are open, how many are limited, and how many have no access. Okay? And yes, having access to a model is important, but if you want to do adaptation on top of a model, having that available to academia is important. We are never going to be able to afford building our own foundation model. Now, you'll hear the word in academia saying, oh, we are building a foundation model for X, but when you look at the scale, it's not as large, and you can go read this report and tell it. I also have a grant with NVIDIA and the AI Institute, and we are building a foundation model. So I'm saying this out of experience. What we are doing is like very tiny and very niche. That foundation model will only be used by a smaller community. But if you see in 2023, There were 149 foundation models, 149. I can't even name more than 10. Because most people, when you say foundation model, what crosses your mind? Can anybody name foundation models for me? What comes to mind? Come on. Yeah. So these are like the top 3 or 4 that everybody knows. But then there are many awesome ones that come out and they do an awesome job. But because the marketing machinery is talking about it, nobody goes and picks up the one that is actually very appropriate for the task. So please make sure that you find something from that 149 as a community and use it and build things with it. Okay, so now we're going to get into this interesting part where I want you to train a model. Those of you with laptops, you are going to go to a website, and then I'm also going to go on the same website. What I want you to do is at least have 1 or 2 things with you. One could be just your own face. The other could be your phone or keys or your badge. 2 unique things that you're going to train this model with. And then we're going to infer and say, can it detect that? And given we had a discussion around imaging this morning, I think it's very appropriate. I was hoping to find something with text in it because you guys would love to see that, but we'll do it with image. How many of you have heard of teachable machine learning? It's from Google. 1 person, okay. Then it'll be more fun. If all of you had done it, then it wouldn't be worth it. And this might fail epically, but we will try, okay? So what I want is to gather 2 things. So there'll be, your badge, your face, your pen, your phone. We're going to train a model, and then we're not going to worry about exporting it, but you can. But then we're going to infer with it, right, all within your web browser, okay? So this is what we are going to do. First, you will go to teachable machine learning with google.com, okay? And if you can't find it, just Google it and it should take it there. And then we're going to start. So whoever is with me, and sometimes your phone or tablets are not going to work, but your mileage may vary. And then if you cannot follow along, go home and try it. Try it with your family, with your kids, your neighbor, people who ask you, how does AI work? You can show it to them and they will be, wow, trust me. So I'm going to start this. I'm going to get out of my presentation. I am going to find my browser. Okay. Whoever is trying with me, how many of you found the website? Awesome. Oh, the show of hands. I am impressed. You guys are awesome. Okay. So click on Get Started. And you are going to click on an image project. You can do audio, you can do pose estimation, a lot of fun things. Okay. And then just choose a standard image model. We're not going to do the fanciness with microcontrollers now. And so we're going to click on this. And the first thing is you can turn your webcam on. So I'm going to turn my webcam on. Yes. And I'm going to change this and I'll say, bottle. Yes. And I can take a bottle and I'm just going to hold it for a few seconds, turn the bottle a few different ways. Okay. I have my bottle. So take your time, train something. And then I'm going to the second class and I'm going to call it pointer. Same thing. All right. How many of you have 2 classes trained or data gathered? This was the data gathering. Anybody finished gathering data for both classes? Okay. So now I'm going to move to the next step where you just say train model. So it's going to do its thing. Give it some time. pretty quick. It trained the model. Make this a little bit bigger. And now you can see if I can infer, and you can see, yeah, it recognizes the pointer. Let's see if you get a bottle. Yeah, it does a pretty good job with the bottle. Let's see if we can trick it with a smaller bottle. Ooh, it still works with a bottle, right? Small bottle. Now let's see if I put my face. Oh my God, it's losing it, right? But I can go add a class and say, now it recognizes me and not as a bottle. Okay. Now you can also go to advanced and you can see under the hood, you know, what's the confusion matrix, what's the accuracy, how many times, what was lost. I'm not going to go through this, but you don't even have to look at this. But the reason I wanted you to go through this exercise, you understand how much data you need when data is less, what errors are, and what is inference. All of this, you can export the model weights, you can give it to someone, you can save it to Google Drive, and it's all one package. So I can just come here and export the model and say, upload it, and it can stay on Google, you can share it from there, or I can even download it to my own computer. So it's really awesome of what you can do with these, and you can do it for audio and other things. How many of you were able to successfully go through this? Damn, that's pretty good. All right. So now here's a tool. So at least you can say you went for my lousy talk and you picked up something new. Okay. So let's go back to our business as usual. Okay. I'm surprised we finished it and there wasn't an epic failure. So if you like this and you want to share this with your, oh, come on, go away. If you want to share this with your students or do things in your lab, or if you are volunteering at high schools, like at high school students, imageteam.org has an amazing amount of lessons. And what I love is that they also go through the basics of how do you learn about machine vision. And then they go into the more advanced part. And then if you go to code.org, they have so much also available there. And if you are looking to get started in this, these are completely non-intimidating things. So it's not like I'm trying to point you in the direction of what I want the high school students to do, but this is even for all of us. When you are worried of how to learn about AI and people send you to random blogs and you get overwhelmed, this is the easy way, and you can gain confidence and learn parts that matter to you. What I loved is what this teacher said, which is the students learn that they don't just have to be consumers when it comes to technology advances they're experiencing on almost a daily basis, but they can actually be creators. And that's what I want to encourage each of you, that you have to be creators in the AI space. Otherwise, it is not going to be what you need. Trust me, it's going to be a bunch of BS that industry will ram down our throats that we may not exactly need. So you have to be part of this. So how do we build this community of practice for AI? This is a textbook I used for many years from Eric von Hippel, which is democratizing innovation. And the word democratizing is always thrown around in different ways. But Eric von Hippel, and this came out in 2005, where he said, if you give the person that is hurting the tools to solve their problem, what they build, however broken, lame, not awesome it is, everybody that has the same pain will relate to it and they will use it, they will suffer. But what has been solved is a core issue that usually people from the outside are not able to see. So when a company comes and tells you, trust me, this works, you need this. But if you get together with 3 people and say, this thing damn doesn't work, let's build something. And this book goes through example after example how people with diabetic pumps have built machine, like improved the machine for delivering insulin in ways that the company could never imagine. And it's become part of products. It's almost like you have to play the role of co-creators, even with the commercial world. Otherwise, you're not ever going to get that into a product, and you don't want to keep bespoke things. So take your innovation, share it with others, and then let companies and others flourish, because sustainability is important. And so don't feel that it's my idea, and if I give it to someone, it's gone. Hey, if you couldn't start that AI company now, I don't think you're going to start it anytime later. So might as well give your awesome ideas to someone. And so in Cybers, that is what we were doing. The cyber infrastructure is where these really shared innovations are ready to use by multiple communities. And so that's how we have a very, very large following of users, because somebody in the lab, there's always one person in the lab who is that computational guru. And the moment that person opens their mouth, they're in trouble, because everybody's like, yep, here's my data, do it. And so they keep quiet. But these are the people that you want, and you want them to be scaling their idea. So you want to scale those people and say, you know what, build this, put it somewhere. I won't ask you dumb questions. Just give me that. But for them to put that together, it's hard. There is no easy way to share that innovation. So cyber infrastructure sort of solved some of that. And we've been really happy to have a community of such early innovators that wanted to share what they have, and they learned the process. How many of you know what is car talk? All right, my people, okay? Or my age group, how about that? Car talk, for those of you who don't know, was on NPR from 1977 to 2012. How many of you think you can repair a car? Right? Okay. One person out of many, right? How many of you can explain what is wrong with your car when it's wrong? Most of you. And how do you explain that? You make noise, right? So these two gentlemen would get phone calls from people, and they would make sounds and tell them what's wrong with their car, right? And you trust your car, you drive it, you take it everywhere, and when it's not doing what you think it should, you know how to explain that to someone. But when it comes to these advanced technologies, suddenly everybody goes quiet. They don't know how to explain why this is making that clickety-clack sound. And so how do you have car talk for AI tinkerers? And so that is what we need, and that is what I want to build, where people who are the Magliozzi brothers can make fun of themselves, the sounds, and why the p-value or why the confusion matrix is more confusing, and how they should solve it. We need that approachable, safe space. And we need to cross the new AI digital divide. The digital divide is here. It's not visible, but it's there. Some of you may have lived through it and not realize it. And in what form does it come? It's access to LLM API keys, running our own LLM, or having access to a GPU. And I just picked this not to, say that this project is not kind enough. It is extremely kind enough. But you go to any discipline, they're using LLMs, and the first thing in the GitHub repo will be, put your open API or OpenAI keys here. And what do people do? Hey, can you give me your OpenAI key? No. That's like, hey, can I have your PIN code to your bank account? No. Right? So you need that. And most people use the free version. You're not going to get the AI key that you can stick into some code. And if you do, it'll run for exactly like 3 seconds before it says, you're done. So you can't do science. And there's no free lunch. So we have to figure out that egalitarian mindset of how do we make this more accessible. And to that same project, they have nicely documented, hey, you want to run your own LLM? This is how you run it. This is how you get access to it. How many of you, like know what OLAMA is, right? Awesome. Those who don't know, make friends with the ones that know, because you should, okay? Because then you are liberated and you can do things that otherwise was hard to do. So this is sort of what we started in our project. We called it AI Verde, which is the virtual explorer for research, discovery, and education. It's unopinionated. We said companies are going to build awesome LLMs. Some of them are open, some of them are hosted, some of them are closed sourced. We are going to use stuff that is running in our labs, or it could be running elsewhere. We have to connect to resources that come from NSF NER, and I'll talk about it, or any place. If somebody is giving you access to a pipeline that you can use, we should be able to bring it in. We should be able to integrate that with institutional credentials. If you're working for us or in a project, you have access to it. It's almost like your digital birthright. You get an LLM for what you need to do. And then the budget spend. How many of you here give access to your students for commercial LLMs? Come on, at least one hand, please. Okay, few hands. How many of you worry what will happen to the budget? Even the ones that didn't raise hand did raise the hand for the budget worry part, right? So it's important for faculty to be able to, or the PIs, to say, here's your $5, go to town, have fun. But if they don't take care of it, that 5 becomes 50 very quickly. And so the budget management was important, especially for teaching, where the departments were like, oh, we can't give you access to OpenAI. That's too complicated. So when we started this, I went with one of my faculty colleagues to his dean and said, okay. The dean said, how much money do you need? And my colleague said, $300. He's like, you got to be kidding me. You want $300 for this class? If every faculty, he like lost it. And I said, give it to him. If it doesn't work out, I will personally reimburse your department, which is the best way to keep administrators quiet, even if you don't pay them. So he said, fine, let's do it. Do you know how much they spend at the end of semester? This was like 30 students. $12, right? But we had spent thousands of dollars in our meeting to decide whether we should spend that money. And so it's important, once you have a framework to do it, the departments will also invest, but right now there isn't an easy way. So we wanted to solve that problem. And then people are building RAG pipelines to do interesting things. So we wanted to also make sure, RAG being retrieval augmented generation, where people create these bespoke things with your documents and only answering from that and grounding and whatnot. And a lot of those were my colleagues who were putting in textbooks that you have certain restrictions and you cannot just make them open. Even though the textbook is open, you're not allowed to ingest and make it available to the world that way. So how does AI Verde look? If I log in, you can see I have OpenAI and I spent 93 cents. And there are different pipelines for different things. And you can see everything from DeepSeek, which by the way is banned in my university, but is available through another university and we're allowed to use that. So that's the benefit of federating things. And so all of this is available to our students. And if I log in, I can see we have a project with Space4, which the model, it's active, what's the start date, end date. When it's done, everybody's tokens disappear. And on the top, you can see who are the members, how much budget, and a prompt library that you create so that everybody's doing things consistently. So if I log in, I can also see Edwin's the TA, Enrique is the instructor, and then I can add more members. And you can again see they spent 1 cent. But you can start seeing the LLM tokens at the bottom where it says, hey, you want to use your LLM, here's the token and here's the OpenAI base. And so you could have any model in the world that you want, but they can go into a program and insert that and use it right away. And then we meet the users where they are. So on the left, you can see I'm using a desktop application. I inputted a map and I said, hey, from this map, extract the names of the buildings that you see and give it to me in JSON format. It's one line. And I'm getting that extraction. I was talking to somebody at, I think it was Sophia, where I said the OCR capabilities of these models is just blowing my mind as to how good it is, where we would spend hours building some of these pipelines and it would be absolutely lame because it was corner cases all the time and never real work. This, it has to be grounded, but it works. And then you can write a piece of Python code and just stick that right there. And then you automate it and go through thousands of images without having to worry. I have 9 minutes. I'm going to fly through the last part. But what we did is we realized that we also had to meet users what they need, where they need. And so the users usually bring in data. We have something called the discovery environment, whether you're Streamlit, Gradio, or whatever is your fancy container, you put it there. The storage understands where it is. It doesn't matter. It comes from Open Storage Network, Google. We don't care. Whoever provides the data is the layer that gives you the productivity. And then Kakao is a cloud automation, which will take it and connect things to other clouds where you have resources. Now, all of these steps are required by the users, but we have to make it easy for them. And so we have it where it's very straightforward for them. And so this becomes their AI platform. Now I'm going to switch gears to, how many of you know what NSF Access is? Okay, well, how many of you know what NSF Exceed is or was? Okay, Access is the new Exceed. It's like you have to change names in NSF to keep money going. iPlan, Cybers, you get the story. So here, it is available at no cost. And there is a lot of awesome infrastructure that most people that need it don't go for it. How many of you are not from US universities? Okay, good chunk. If you want, make friends with people in the US universities. They can apply for the allocation and then include you. So one more reason to be friends with US so far. Okay. And then you can see it's very easy to get those resources. JetStream is one of my projects under that with my colleagues at Indiana. But you can get access. The H200s are getting installed as we speak. We already have a lot of A100s. If you want to teach a workshop, you need GPUs, please go, apply for it, use it. If you have problems, email me. But I want you all to use this. I don't want I welcome everyone, but I don't want the ones that know how to do it. They come and take away everything. It's the ones that don't know about this and they need to use this and build your community of practice where you say, well, we don't have GPUs and my university won't let you connect. I don't have money for this. $0, get together, come talk to me and build what you need to. So here's an example. How many of you use Colab? How many of you need bigger GPUs in Colab? Right? You can go look up this webinar. You can start your Colab, start a GPU in JetStream and connect to it. And you'll be using an A100 to run your analysis. So go to the NAIR pilot. How many of you know what NAIR is? National AI Research Resource. It's now getting crowded, but it was like shooting fish in a barrel for a while. So I did get my fishes out of it. And so here is our work in our AI Institute, where this is a massive model that we built. You heard this morning from Imageomics. We actually did get some inspiration from their work, but our next generation work even connects the things that are insects with that are very agriculturally relevant, but the mitigation strategy and everything else, and it connects all of that together. You are always going to have the need for doing things on a desktop. And this is on the horizon. They're already taking early orders, anywhere between $3,000 to $4,000, but it's worth it for the power you get. And once the commodity comes in, it'll get, So here is sort of the training part that I was telling you about. If you go to the Data Science Institute, every day of the week, there is something we talk about, and it's 1 hour sessions, and our students get access to learn something that's not in coursework, but they need it. How to do something with PyTorch, how to do something with NLP. And here you can see foundation open science skills, but if you read at the end, end-to-end ML workflow. How do you do it? How do you build it? And these are all students from information science departments. Same thing with NLP. You learn how to use Colab, you learn how to use Hugging Face. And I saw this from colleagues at EBI. I am so happy to see that they have these things. And you should be attending this. Please, please do. And finally, I'm going to give you a real world example. Here is one of my staff who just gave a keynote last Friday at a drone day conference, and he put together what is his compute pipeline, what is his storage pipeline, his processing and analysis and sharing. And you can see for teaching, he uses Verde because he wants his students to use LLMs, Google Earth Engine. He uses Campus HPC. He writes his cacao recipes and uses something in Amazon Cloud. So all of this, Jeff, for 17 years, has been a hardcore geospatial. He is a remote sensing person. Never knew a lick of AI or Python when he came to us 2 years ago. And now it's him. So each of you can be the Jeff. So don't feel that this is out of scope or you cannot learn this. You absolutely can. And then here is Leonardo, our student, and this is out of one of my AI grants we had, where we created this AI zone. It's a booth. It's a traveling booth. We take it where, and people have never seen a real GPU or a little Jetson Nano, and they learn how to program something on it, count beans, or even do teachable machine learning. You can see Leonardo is teaching the students there. So I'll end by saying, knowing has shifted from being able to remember and repeat, but is able to find and use. And you guys need to find and use the resources. And this is a slide I always end with, which is I see everybody as superheroes. And if you want to go fast, you go alone. If you want to go far, you go together. And you need to build that community and go far. And that's what inspires all my projects. Thank you. We have 3 minutes, right? Or 2 minutes and 58.
Any questions? So thank you. That was really informative, and I might add really entertaining. So I appreciate the balance there. It was really nice to learn about all the stuff that's available in the public sphere. But I work for a pharmaceutical company, and we're very protective of putting our data into the public sphere to be analyzed by these tools. So my question is my option for this incredibly fast-moving field that I have to keep creating internal instances of each tool?
Good question. So depending on, given you come from an area where security and privacy is treated differently, and the custody of data is a different conversation. I don't know if your company has like a presence in the cloud or on-prem, but if you do, there are the tools that I talked about at the base layer. You can remove the physical infrastructure, but the tooling itself, the software, is all open. Those models are also all available. So if, let's just say for conversation's sake, you were an Amazon customer, Amazon Cloud, you have SageMaker, which will give you the same things, and then you can have the same models and do the same thing. So it's just that you will swap the underlying layer to Amazon and their equivalent, but they all use Jupyter notebooks in 5 different ways. They all use OpenAI for calling their own models, and they will sell you the model, the LLM access the same day.
Thank you.
Yeah.
Thank you, Nirav. That was a very inspiring talk. I wonder about a couple of things. You going back to the Gartner cycle, actually going back to before that. So as you know, those of us who dabbled a little bit in AI, or even worse, saw others do it not very well, know there are a few very, excuse me, obvious pitfalls: overtraining, leakage, bias, things like that, that compound to having a product that seems incredibly correct and working well, but it isn't. And my worry is that without adding those cautionary tales as a strong component in AI for everybody, or democratizing AI, we will get something that we can get, like a populist AI, like we have populist democracies, right? Which are not really democracies. We'll get a populist AI where people are all doing AI, but they're not doing it right, and they're getting wrong things out of it, and that has impacts down the line. So I'm wondering if you have any thoughts on how to incorporate to have a robust democracy as opposed to a populist democracy of AI.
Excellent question, and my view to that is, if you don't know how it works, if you don't know how democracy works, your participation in democracy in itself is flawed, right? And so applying the same thing to how do you educate somebody about democracy in general, right? And then you participate in it. But if you are on the sidelines and you just say, somebody told me to do this, hence I'm doing it, also becomes a challenge. And that's why I said, you have to form your community of practice, right? If you just say, we're all going to build something immensely complex by ourselves, we don't need to talk to the statisticians. They always like rain on our parade anyway. Let's not invite them to the party. Then you're already in trouble. But if you say, hey, can somebody bring in a statistical machine learning person? Can somebody bring in a computational linguist? Or so that diversity within the group of people that are trying to do something in your community of practice is important. And often these things are like 80% solution. By that, what I mean is they'll get you somewhere. And if your standards are like, I'll live with 80% and that's okay, that's a different conversation. But if you are like, hey, I'm going to help people and I at least need 90%, that 10% is going to be what is going to virtually kill you. But then you have to be prepared for it. But if you never understand that there is a 90%, you think 80% equal to 100, that's the part that you're talking of. And that will only happen if people get involved in that activity where they can point out and say, no, this AI can do better. This is not acceptable. This is doing something else elsewhere that has been achieved. Why can't we achieve it? Where is it the limitation? Do we need a data campaign? Do we need to curate our upstream data better? Or do we need to bring those? So those kinds of conversations will only happen if the community is engaged, because the subject matter experts are keeping an arm's length from AI, and that's scaring me. And that digital divide cannot be there if you want to be productive and adopt it. So hopefully this gives you my stand.
Thank you very much. And we're gonna continue the session. And Christina, we will present like on the lab bench to web.
All right, good afternoon, everyone. My name is Christina Parry. I'm from Sage Bionetworks. And at Sage Bionetworks, we create a portal called synapse.org, where we host data and manage the sharing of data. So I'm excited to get the opportunity to talk to you about how we're trying to make data more accessible. Beyond creating synapse.org, we also have portals, and these portals span from disease domains from cancer, Alzheimer's disease, neurofibromatosis, and here's just an example of what our portals look like. So where are we today? Today on Synapse, we have about 4 million gigabytes of data, 90 million files, and for downloads, sorry, it's a little delayed. Okay, sorry. And we have about 13 million files downloaded per month. And this equates to about 4,400 users are downloading data per month. But how can we enable interdisciplinary communities to use our data? And so when I'm talking about interdisciplinary communities, I'm talking about some machine learning scientists. So for over 15 years, Sage has hosted challenges to draw machine learning researchers to our biomedical data sets. And these challenges are called dream challenges. You might have heard of them, and they're really a great opportunity to get more eyes on data, fast results, and they have high impact. However, these are short-term events. They're a specific topic or data set, and it's a large organizational effort. So what can we learn from our machine learning community to scale our exposure of data sets? Here's an example of websites you may have heard of: Hugging Face, Kaggle, OpenML, Google Dataset Search. And one thing that is really up and coming is all four of these dataset platforms either generate or search using croissant dataset schemas. So what is this delicious croissant? Croissant is a schema that enhances usability of datasets for machine learning by making them more accessible and easier to digest. So if you've heard of schema.org, this is a standard metadata structure that is used to enable search on Google. And it's one of the aspects of making your websites more findable. Croissant is an extension of schema.org. And so if you're looking at the top portion, what you're seeing is the schema.org portion that's providing metadata such as keywords, description, citation, license. And then Croissant describes the structure of the data, files, and metadata to ensure compatibility with machine learning algorithms. So our goals, I'm going to start actually on the final goal first, and that's to make data accessible beyond domain-specific portals and instead make it accessible on Google Dataset Search. And I'll talk about the next two and kind of go backwards in time. So let's start with this third one. So this is what it looks like. Let's say you have a data page. This is the NF data portal, neurofibromatosis. You have a data set here. And when you're inspecting the page, you right-click, click inspect. You can see that we have this schema.org snippet metadata that's applied to the web page. What this looks like, if you are successful, you go to Google Dataset Search. Here I'm just demonstrating. If you type in nf.synapse.org, we have a few data sets that have recently popped up on Google Dataset Search, and that's because we recently implemented this schema.org snippet. However, I'm clicking the croissant button to show you this is work in progress. So the next step is that we're adding this croissant filter. So stay tuned for this part. The first pilot of croissant datasets is expected in June 2025. We're working to release 32 datasets in the neurofibromatosis disease domain as a proof of concept, and then the future releases will expand to other disease domains. And so the second question is, how can you annotate datasets with standardized schemas at scale? So what we're working on is to develop human-in-the-loop AI curation tools to ease the annotation burden. And what I'm talking about is at Sage, we have a lot of community contributions of annotations from researchers themselves. So here's an example of someone just manually filling out a spreadsheet. Obviously, this can be really time-consuming, prone to errors, and most people just really don't want to do this. So in the future, what we're working on right now is human-in-the-loop curation. This is like a really fast animation of kind of what it's going to look like, where you have a chatbot, you're interacting with a spreadsheet, you're able to import publications and text in order to like help the person annotate. It's aligned with our data model so that they know that it's the correct term. This is our actual proof of concept that we're working on now. So I'm just going to talk through what this is. This is a real chatbot that we've created. And so what I'm asking it to do is just, it's called Cindy. It's what can you help me with? And so Cindy can help with querying data tables, data curation. The key thing that I'm showing here is the data harmonization aspect. And so I'm clicking a button to say we want to harmonize our data. And I'm showing a table on synapse.org that is kind of like a table. Think of like an Excel table that's full of metadata. So I'm asking, can you help me annotate this data? It's saying, sure, I can help with that. I'm asking what columns are there. And so it's going to give me a list of columns. This is a neurofibromatosis example. So right now we have assay, diagnosis, and tumor type. And it gives you a little bit of the sample data and how it's going to map these terms. So I'm saying harmonize the assay column. And the next step, it's going to query the table, and then also is talking to an AI model. We have partners from a company called Netrius who actually built the model. And so it's calling their AI models, which are giving you the insight as to, okay, let's say, for example, the person typed in whole genome sequencing in the table, we want to change that to like the particular ontology term that we're choosing as like the real one that we want. So this is just like the example of how it's converting to that standard ontology. And so then the first part, so this is kind of, again, going back in time, how can we develop data models and train AI models at scale? And so for this part, we're implementing core models within and across disease domains. And as we all know, creating consensus in science can be very complex. One group might call it a dog, the other group says it's a puppy. So what we're using is a program called Core Models. I do want to take a step back. We actually create our data model in LinkML, and then we're creating like a compatible pipeline that imports it into the software called Core Models, which we've had a partnership with them for about a year now, in order to organize the models. There's inheritance, taxonomies, the ability to visualize the models. And so with this, the main project that I'm working on in this currently, and the first mapping's expected in June 2025, is we're collaborating with 2 neurofibromatosis research clinicians to align terminology in clinical trials and research studies. And this will provide harmonized data sets and provide a larger curated clinical data sets in the rare disease community, which is like a very important need for this community to have larger data sets. So the key takeaways, each step of this, I want you to think of it as like they depend on the previous one. So this is why I called the talk from lab bench to web process. First, you need to create consensus. So establishing standardized data model for your field, expand it by mapping related data terms and making it interoperable with other fields. Next, we're reducing the burden on researchers by providing this human-in-a-loop AI curation tool. And then finally, enabling access. And this, all of these terms and data models, they all feed into eventually the ability for someone on the web, a machine learning researcher, a student from across the world, in order to find the actual biomedical disease domain data sets, rather than having them within our portals and not accessible for everyone. And so finally, I'd like to acknowledge this has been quite a collaboration between a few different groups. So I've listed the folks at Sage that primarily have worked on this. As I mentioned, we've partnered with a company called Core Models. And so just, they're helping us with some of the data modeling aspects. The AI models are built by Netrius. And then I've highlighted the clinician researchers that we're working with. And then also the Croissant working group, which I'm a part of, is a part of the ML Commons, kind of like bigger organization. And then finally, we have funding from ARPA-H to do the AI work, and then our neurofibromatosis funders. And thank you very much. Happy to take any questions.
Thank you, Christina. Any question? If not, I have one. Yeah, I'm just wondering, because I mean, at the Institute of Bioinformatics, some of our data sets that is being built, the database and so on, part of it, we try also to put being available and searchable to the Google data set.
Mm-hmm.
But actually we notice after, like maybe 2 years from now that the user base that comes from these resources is not that significant. That I'm wondering, because probably also many life science don't rely, maybe they don't even know that this exists. Then I'm wondering if in your case, it was like a better user base coming from the Google data set.
So yeah, that's a really good question. I still really don't know the answer to that. Part of the machine learning working group is there's folks from Google Dataset Search there. Mm-hmm. And so it's helpful to see that that's important in their community. I guess, again, I want to highlight that we're trying to go places where scientists might actually not go. And so I think from the machine learning community, these websites like Hugging Face, Kaggle, potentially Google Datasets, eventually, like we might even want to reach out to like Hugging Face and like put data sets on there if we can get the governance issues, because right now Synapse holds a lot of like the governance because some of it needs to be protected. So that's kind of the challenge as to transferring data. But yeah, I think there's more studies that need to be done with like that user interface. The one thing I failed to mention is that the Cursant files themselves will also be available on our portals. And so besides having the data sets show up on Google, another advantage to having the Cursant file is that someone can actually download it and use the data set and import it into their machine learning workflow. So
Okay.
it's kind of like killing two birds with one stone,
Mhm.
where it's enabling accessibility and that downloading that file.
Yeah, I agree.
Yeah.
Thanks a lot. Sorry, you have another question.
Yeah,
Sorry,
yeah.
I didn't see.
So I have a question that, so these are like a simple Excel queries that you have built on the chat box. What is the possibility of looking into the relational searches where you can integrate information from different sources? rather
Yeah.
than a single Excel table. And
Yes.
The second question is, how long are you going to maintain your Excel tables and making it shareable to the public?
So for the
Yeah.
first question, we're also looking into using unstructured text to import information to fill out those tables. So in the example I showed today, we're starting with a table and then just like converting that to another table.
Yeah.
But yeah, there's another pipeline that I didn't show, and we're working with a few people on that, where you could import publications and text to help you annotate as well. And sorry, I didn't catch the second question.
So my question is that, what about the speed of this? Because it seems to be a slow process as compared to relational database queries or queries that are, for example, Neo4j cipher queries, right? So this will be extremely slow process, Excel-based queries.
Yeah, so yeah, I say we're working on it. The process right now is really aimed at annotating data, and the next step is actually more like a chatbot interface with a template. And so it'll be kind of like filling out all of the columns at once. So yeah, maybe I'm happy to talk after to get more clarity. Thank you.
Thank you very much.
Thanks.
Then our next speaker is Hande.
Hi, everyone. Can you hear me? Okay. Hi, everyone. I'm Hande Kucuk McGinty, and today we're going to talk about our new adventure, about biomarkers of aging. And for this project, we collaborated with a startup, Biomarkers, and we're actively continuing our collaboration with them. So before we talk, I'm going to briefly introduce myself. I'm an assistant professor at the Department of Computer Science at Kansas State University. All my degrees are in computer science, but I've been working in interdisciplinary projects for over 2 decades now. And before joining K-State, I was working with the USDA, so food ontology. And before that was my other life in collaborative drug discovery and drug discovery realm. And let's move on to biomarkers because we don't have a lot of time. I have a brief description of biomarkers, but I know that I'm among ontologists. So this is an active definition, okay? So please don't take it literally just yet. And for those of you who are affiliated with the phenotype ontologies, we are in sometimes disagreement on what a biomarker is and what a phenotype is. I'm not going to go through that either. So you can safely assume that the ontology backhand for this work is an application ontology, and it was really geared towards biomarkers' needs and their questions and their applications that they're building actively now. So for the biomarkers of aging, the realm gets even more crowded and unruly because aging biomarkers, from omics to functional biomarkers, have a wide range of things that they want to talk about, and they understand it differently. And there are so many aging clocks, you won't believe it. I didn't know that was a thing. It's amazing. But collectively, we're helping billionaires to help them live forever, So we'll see how that goes and if we can make that happen. But the problem that we're trying to address with this work is that all the biomarkers that they were trying to talk about aging were really disorganized. And it was really hard to make connections among these biomarkers. And, this work does not address causality because that's a whole different ballgame. But even the basic connections and the correlations were poorly described and really not well categorized. So I decided we'll try to help them. We collected some data. We performed some statistical analysis on the data, create a small application, not ready for scrutiny, using Streamlit. And then we use our existing methodologies to create the biomarkers of aging ontology, again, application ontology. And then we did some more exploration using algorithms and embeddings. So for the data collection, and I want to mention that I was very happy that we've been talking about human in the loop, because this has been the niche that my team and my work has always supported and was a part of in terms of methodologies go for ontology building, because especially when we're talking health and bio, right, and when we're talking about pharmacology and companies where there is actual drawbacks of making a big mistake and it's not just research, we really want accuracy. So the combined data sets are coming from enhanced data, looking into the data from different patients and combined through their IDs. And the statistical analysis is based on how these biomarkers, filtered by other biomarkers, are correlated to one another. So if I were to look at my blood sugar, changing the ranges of my BMI, you would see that the biomarkers either work or move in the graph closely correlated to one another, or they're just looking at different patterns, and then we think that maybe they're not so correlated. So based on that first initial correlation and running this, findings and maybe there's a statistically significant way of these correlating these biomarkers, our domain expert kind of gave us a feedback, and through that feedback, we then decided that we're going to build our knowledge graph. You know what knowledge graph is? I'm not going to give the definition to this graph. So we use my very memorable acronym NARM methodology for this methodology that really keeps the domain expert in the loop, talks with the domain expert, looks at the expert curated data, and really uses the existing ontologies and recycles that vocabulary actively before you start creating your own model or your own ontology to support that. And through this methodology, we have started kind of building our own templates, very similar to the templates that OpenFoundry uses, but slightly different. And we created our categories for the biomarkers. Again, that the categories that EON biomarkers were most interested in, and based on the biomarkers that they were most interested in, and decided that this is a good model for us to look into biomarkers. So according to EON biomarkers, are really needing an FDA category, a way to identify and really way to, I know this is hard to read, so I'm just going to go ahead. So for the FDA categorizations, we really want to see about the risk and diagnostic perspectives of it. Is this an invasive? Does this biomarker need an invasive test or not? Oh, sorry. And let me talk a little bit about the sample sources and where the sample is coming from, correlating with the tests and everything else. And we're also really interested whether this is an aging biomarker, a disease biomarker, a system biomarker. And as I was saying that this ontology being the application ontology, I want to give a shout out to Raja, who's going to present tomorrow, and Darren. They're in the different Georges in DC area, but they're in one of Georgetown, George Washington universities. They're actively building a more comprehensive biomarkers ontology, and we're collaborating with them to see how we can contribute with the aging biomarkers to that. Moving on to the next step that I find very important in ontology building and knowledge graph building, the database backend. I love Excel sheets and I appreciate all domain experts use Excel sheets. I cannot use an Excel sheet to save my life, I don't think. So we really enjoy building database backends to our ontologies, knowledge graphs, so that we can really use this data and the databases in various applications. We choose Neo4j, and we chose Neo4j for this data. I know it's not always the choice in the community, and there are so many long discussions about why you would choose it, why we wouldn't choose it. This is not capable of this, that. So there's a whole discussion behind it. The reason why we choose Neo4j really is because it is very friendly to our other applications, and it's a versatile tool in our experience when it comes to querying, and it's actually scalable for large graphs. And so because of those capabilities, we have a Neo4j backend to the knowledge graph that we're building. So semi-automated ontology, but then the semi-automated, because the domain expert still is in the loop when we're building these things, because accuracy matters, has been a part of this methodology long before, but the LLM aided automation is the new part. The Olive, much better acronym, wouldn't you agree? Yes, than NORM, is using a number of different input sources, still using the Neo4j backend, and then creating the knowledge graphs based on that. So for this, we again created a very not scrutiny ready UI to kind of see what are the different graph things that we like to do for our research. You know, creating and extending the graphs, maybe getting insights from the graph, maybe merging a couple of different graphs, because the methodology is really designed to look into how we can create ontologies that are concordant and play well together so that we can keep building this, because as we know, science and biomarkers and everything in bio keeps changing, just like everything in AI. So here are a couple of screenshots from the different data sources that we use and use to run Olive. And quickly gonna run through these. As I mentioned, we didn't only do the LLM-aided approach to help create this ontology, but also ran depth-limited search algorithm to see if there's any other relationships that we can add to the mix. And through this, so the way depth-limited search works, that you have a depth limit, and then you have a starting node, and then from that starting node, your algorithm traverses the graph to find new relationships that you may not have discovered before. Through this, we discovered about 500 new relationships that we haven't discovered before. And using the embeddings, we then added yet another 147 associations that we haven't been able to find before using any other approaches. And we do to, you know, validate this data. I'm over time, so this is an ongoing research, and of course, this is my team. This is our most recent picture. One of my students is here, Sohail, and happy to take your questions. Thank you very much.
For one question.
So when you got those biomarkers for aging, you said you collaborated with a company.
Yes.
So is that company giving you list of biomarkers? So I'm just trying to understand, where are you getting these biomarkers from? Are they coming from?
Yeah, yes, they did give us the list of biomarkers, but they are from the enhanced data sets. The biomarkers are coming from the enhanced data sets. So we are looking at the biomarkers that are already measured in the enhanced data set.
Okay.
That which is public.
Okay, thank you.
Yeah.
Thank you again. Then we're gonna have like the next presentation and like next applause for thanks. Okay, I thought, yeah.
I'm here.
Okay, then sorry. Then, yeah. Go ahead.
All right. Well, thanks for attending this talk, everyone, and thanks to the organizers for having me here because I'm excited to talk to you about LLMs again, which is something that I've been very passionate about lately, as we've all been on this wonderful adventure. If you can believe it, it was actually 5 years ago that GPT-3 got initially announced. It wasn't immediately online or immediately usable, but since that time, our adventuresome and open, or maybe OpenAI seas, have turned a little bit stormy, and probably for good reason, because there's a lot of distrust in those seas. We've heard that domain experts often want to take an arm's length from the LLM world, or maybe even broadly AI. And well, I mean, that's fair because there are perils, and I'm going to specifically focus on hallucinations and things that LLMs may just make up wholesale. But I would like to say, if I can begin the metaphor that I established in my talk title here, that human curated resources are in fact the lighthouses on the edge of this stormy ocean, and they help us to center on what is real and help us to avoid crashing into the rocks. So I'm sure everyone in this room is at least tangentially familiar with LLMs, but I'm going to remind you that there's a distinction between the model itself, which is essentially just a collection of the probabilities of tokens or words or otherwise sequences occurring next to each other, and the interface that you access them through, which in the case of something like GPT or even other models like Claude, often has a interface in front of it. So we call that Chat GPT, and that has kind of those additional guardrails, additional modifications to the way that you're actually asking these prompts or queries. So sometimes the results that you get out of something like ChatGPT don't always exactly reflect what you get from a raw model. But in either case, there is and there remains the risk of hallucinations. Sometimes these end up being called confabulations, but what they really end up coming down to are these instances where the output that you get from these generative models looks believable, but really doesn't have any basis in reality. Or perhaps in a worse case, it has a partial basis in reality, and it's difficult to distinguish between the falsehoods that have been introduced and the real parts. It's kind of a tall tale. And I like to say this because LLMs are grounded in language rather than facts. They are trained on language. They are trained on sequences that represent language. They are not necessarily trained on the facts behind those languages. And in fact, the chart that I have shown here is from a hallucination leaderboard. This is actually based off of very short image summary generation. And we see that some of the more recent models, like GPT-4o, seem like they're marginally better at producing fewer hallucinations, but they are still out there. It's getting better over time, but yeah, it's still a bit of a challenge. So what weaknesses do LLMs have in actually doing biocuration? So if we ask GPT-4o to provide corresponding identifiers, we give it the text and we say, okay, I just want to know the gene ontology IDs for each of these terms. Well, I tried this just yesterday, and 4o, despite being one of the better models on the market right now, gets every single one of these wrong. It just kind of makes up IDs wholesale. If you go the other way around, it will also make up gene ontology terms for you, despite the fact that, yes, it has been in contact with the entirety of gene ontology in its training. And part of this is because, well, this is just not a core competency of LLMs. Again, they're not trained in fact, they're trained in generating sequences. This happens with other ontologies, other models. It even happens when you include things like integrated web search, although the search does help, and I'll allude to that a bit more in a short while. So maybe the big question here is, can LLMs really reliably translate unstructured scientific data? Let's say you're starting with some of that unstructured data, even the more like the multimodal or the image data that we've heard about earlier today, and maybe we have schemas or data models that we want to adhere to. Maybe we want to be able to link to other resources, as is often common in biocuration, and more importantly, we want to be able to ask questions about the results that we get. How do we actually go about doing that? Well, the first thing I'm going to talk about here is this tool called Spires. This is actually getting a little bit long in the tooth in terms of LLMs, as we published this last year, and that feels like an eon ago in AI time. But the basic idea here is that if you start with a data schema and that's written in LinkML, you can use this Spires method as part of the OntoGPT software. All of this is publicly available online to populate that schema. And that could be extracting individual terms, extracting more complicated concepts. That could be filling out entire parts of an ontology or any other kind of structured knowledge base. So again, that's freely available through OntoGPT. And importantly, that does not require using something like OpenAI's models. You can use it with local models. You can use it with other models. If your institution has some kind of local AI hardware, it will generally work with that as well. So as an example here, even if I use OntoGPT with the Spires method and Llama 3.3 model, and I just kind of pointed at a paper, in this case, this rho kinase inhibitor related paper, and I say, okay, well, I want you to extract several different types of Go terms. Well, in this case, OntoGPT and Spires are actually capable of doing that because they are directly linked to the identifiers in the gene ontology. They are aware of that, and they do not have the LLM solve that part of the problem. The LLM is only asked to extract the terms, and then the software, in this case, OntoGPT, tries to find the corresponding gene ontology term. It is not perfect at that. Often it will extract things that look very much like them. I see that as a feature rather than a bug, because in many cases, this either suggests that maybe your model could be a little bit more refined, or there are simply other details in your input text beyond what might perfectly match to an ontology. So there's a whole number of other applications that we developed since first releasing this method, including for extracting medical actions from literature. These could be things like diagnostic processes or other clinical actions. There's a preprint on medRxiv about this that I think is actually quite nice. Others include, as part of the Monarch Initiative, we're trying to extract information about micronutrients from the Micronutrient Information Center. So these are details like, okay, iron, what does it do in your diet? What is it good at treating? These are all kind of details that would be great as part of a larger knowledge graph. Additionally, other clinically related things like extracting data in the phenopacket format that I think may have been alluded to earlier. And then even more broadly, applications in environmental sciences where we have data sets like the ESSDive database at Berkeley Lab, where being able to just extract harmonized information from existing data sets can lead to better search. Now, I'll highlight a couple related tools that are slightly more recent and very focused on highlighting what we can do to help biocurators do in the process of doing curation without completely replacing them at their jobs, because that is certainly not any of our goals here. We recognize that, you know, the human part of the equation is one of the more perhaps the most valuable part of this process. So one of our newer tools is this one called Curate GPT. As you can imagine from the name, that's focused on curation, but this is largely agent-driven. It has an interface in Streamlit. We're big fans of Streamlit. But the focus here is on doing retrieval augmented generation. So that's when you provide the data that would help out your LLM-driven agent. This could be an ontology itself, where you're going to say, okay, this is the structure of my ontology. Here are what the other terms look like. Now I want to create a new term based on this paper or this amount of information that I have. Or in some cases, like our SiteSeek agent, you can go and search the literature for information that would back up that claim or that entry. More recently, we also have continued to go in this direction of agent-based LLMs with this tooling called Aurelian. That's also online. This is based around kind of a Gradio interface, but also works on the command line. But these agents are a bit more kind of task specific. For example, this is one that really just does lookup for the Amigo service. So you can say, for example, you know, I have a protein ID here. What are some annotations that I can get for that would make sense? And because it's interfacing with Go directly, we have reasonable confidence that the IDs that it's using are not just hallucinated. Now, there's a whole bunch of other tools in there, including one that'll do mapping between terms. And again, it's going to look up ontologies directly, so you can be confident that they are not hallucinated. So I encourage anybody to go check out those tools. Let me know if they can't run on your machine, and I'd be happy to give you a demo. We have others as well. Some of these have been folded into Aurelian or other toolboxes since then. Yeah, feel free to ask me if you'd like to know more about any of those, because for now, I'd be happy to take any questions.
Thank you, Harry. We have time still for one question.
Yeah, oh, sorry. Over here. Yeah, so I think thinking back to the keynote speakers, Gartner hype cycle chart, I'm curious what your thoughts are on multi-agent approaches for doing this. Now that you have your little library of agents to do all these specific tasks, how are you experimenting with combining them to kind of do the whole soup to nuts process of curation, whatever that might be?
Right. Yeah. And I think one of the big challenges in kind of maybe the first cycle of people adopting these LLM based methods was that it was very open-ended. It was very easy to just say, okay, well, I know what I want to do. How do I phrase this to the LLM in a way that gets it to know what I want to do? So at least with the agents, we can kind of essentially pre-train it. Say, hey, okay, this is what the task is. So I think kind of the remaining glue is maybe to have a consistent framework for defining how these agents work together. And I know there's definitely been work in this area, and even in cases where you're kind of getting different agents based on different models to work together, and that's a really exciting area lately. But I think maybe we need one specifically for biocuration. It's kind of aware of the way that biocurators like to work, and more specifically how we can kind of get these tools to work together.
Okay, thank you very much. A second round of applause to Harry. Thank you. Now it's the person that couldn't come. Then he sent a recording from a spaceship because it's from NASA actually, apparently. And I'm kidding. Okay, hopefully we're gonna have it set up in a few.
Quick announcement. While we load the presentation, I would like to mic the last speaker of this session.
It's Sushma. Yeah, you are there. Yeah.
So if you could come see me at the top of the stairs, that'd be great. Right here.
Otherwise, yeah, please. If you can go there, thanks.
Hello, everybody. My name is Walter, and I'm a research scientist here at NASA Ames. Sorry I couldn't be there in person, but I'm here today to just talk to you about a little bit of the way about how we curate data here and some of the tools that we're developing to help curate biological data, specifically data that comes from space. So just to give you a little more background, I work with the Space Biology Research branch, and our sort of role is to study how life adapts to space. And we do that through spacephone experiments, ground simulations and analogs, and we evaluate the different types of risks like microgravity and radiation. We collect all this data, and then we create a repository for it, the NASA Open Science Data Repository. And the NASA Open Science Data Repository, or OSDR for short, is comprised of 3 different branches. We have ALSDA, which stands for the Ames Life Sciences Data Archive, which is responsible for telemetry data, imaging. We have GeneLab, which is responsible for molecular and omics data. Users can upload, download, share, store, analyze spaceflight and spaceflight relevant data from experiments using model organisms. And we also even have a biobank, the MBIS, NASA Biological Institutional Scientific Collection, which is a biorepository of non-human samples collected from these NASA-funded spaceflight missions. We make all this data accessible to the rest of the scientific community, and we try to ensure that it's fair. And these portals or these data repositories allow us to get maximize the scientific return on a lot of these experiments. It's not every day that you get to do experiments in space. And so having these tissues and these data available to the rest of the scientific community is a very important part of our mission. And as you can see here, we sort of span different types of agencies. We have different organisms, different types of studies. We have over 160 terabytes of data. I think we're almost at 1,000 data sets, over 500 studies. And so like any data repository, we run into the same challenges as any other type of industry or scientific repository, that a lot of the data we collect ends up in these different silos. And so by using FAIR principles, we try to minimize these silos and have the data accessible and interoperable, reusable, and findable. So that's kind of like the background of the mission and what we try to do. Now, the way that we view, this whole data ingestion process is like an ETL process. You have extract, transform, and load. And the question is, how can we sort of automate this process? And at what points throughout this pipeline are we comfortable with using AI? And so kind of the gold standard or the holy grail of what we're trying to do is essentially this. We have these different studies, we have drafts, we have tables. How do we take all that information and create these formatted tables or these formatted JSON files from just using the raw data? And so a lot of that involves developing parsing tools, libraries, and things that leverage large language models to help us to get there. And so one of the initial tools that we developed over the summer last year is sort of a data alignment and verification tool. Now, here on the left-hand side, what you're looking at are these different columns that a PI that we require for our data repository. So you can see here that we need like euthanation method, biospecimen category, sex, genotype. And here on the second column is what the PI or the person doing the experiment submitted. You can see for some of these, they're very similar, right? So it's easy to parse the data and try to align it pretty accurately. But there are points or certain headers where the actual name might be slightly different. It might be misspelled. It might use a different word. And for those type of things, we can use programmatic solutions like a Levenshtein distance to measure how two sequences are. If we get to, for example, this example here, where we have dose 1, but maybe they use a different word like treatment 1 dose, we can kind of leverage a large language model to find the semantic match. And it's actually how we started developing a lot of these tools and sort of the AI curation tool that I'll talk about a little bit at the end. So a lot of this is just applying a schema to the output of the large language model. So when we try to, when we ping it and we say, hey, we need to figure out maybe the chemical used for dilution, we impose a schema to ensure that whatever comes out of the large language model follows that schema. And if it doesn't, that's fine. We can move around, we can move along and leave that to our curator later on. And then it's making these tools accessible to the rest of the community, people who might not be well-versed in coding, trying to build these tools or solutions for them to make it easier for them to be able to manage these data sets. Over here, one of the biggest things that we sometimes deal with are tables. So you can see here that we might have a table that has a lot of mini tables inside of them. And so some of the tools that we develop allow us to sort of separate these tools by looking at pivot points in the Excel sheet and be able to split them, and then maybe using like a large language model to summarize them. And so another type of data set that we work with are images. And so here's sort of our first proof of concept. We're trying to show that we can use all these data images that we have in our repository and create summaries of them. And so if you look at here, we load a few images and we ask it, hey, what are these images? What's in them? And so we have a large language model or a visual model look at these and be able to create these summaries at the bottom where you'll see the actual, what the image is all about. And then it creates keywords. So then when we try to search for these types of images, we have a lot more to go by, allowing us to sort of minimize the search space when we're looking for a specific image. So another thing that we're using in terms of leveraging AI and large language models is automated tagging. So a lot of the data that we have in our repository don't have certain fields because, you know, no one could have predicted how large language models were going to blow up or anything like that. Or there are some fields that we might have missed when we initially created a repository. So one of them is whether some of the data sets that we have involve mice or actual human astronauts. And so one thing that you can do is that you can enrich the data that you already have by running these studies through each large language model and having it tag it based on the context of the study. So for example, it might not be clear to us that certain experiments involve astronauts fed by just looking at the metadata tag. And so the large language model can generate these accurate tags. And then that gives you the ability to be able to explore your data set and use those tags to leverage more information from the repository. So here we can see that you know, we have all these sort of breakdowns of what our data sets look like. But now, you know, with these additional tags that were generated using an AI model, we can kind of get better insights. Over the summer, we've had interns who have also leveraged these AI tools to generate graphical abstracts. So we give it a study, we give it raw data, and the AI model can kind of extract the information it needs and create a visual about the type of experiment. So here we have mice that were radiated at Berkeley lab. And so the model was able to extract the level of radiation, the types of tissues that were harvested, the amount of time, and then it creates this graphical abstract just based on that information. Another really cool thing that these large language models can do is it allows us to discover data sets that might not have been obvious by just using a search bar. So it can summarize and explain and can sort of point you to other studies that might have been more relevant based on the search that you were looking for. So it allows you to use natural language to be able to find these data sets. And so here we kind of have an example of our chatbot that we have employed in our repository, where you can kind of ask it, like, you know, are there any bone density loss in face-like data sets, and it kind of points you to where you need to go, which is pretty cool. And so everything that we sort of talked about is something that we're developing now. So this is sort of the front end of this tool that we've been developing for the last couple of months, that allows us to be able to curate data based on the data sets that we give it. So if we give it images, tables, PDFs, it can extract images, it can extract text, it can extract different types of information and create these summaries and these keywords that you can then look on the right-hand side and get a sense of what you're looking at. And it creates these formatted outputs. So it gives you a summary, gives you these JSON formatted outputs and certain keywords about what this image is all about or what this document's about. And the idea is to be able to curate the data set for your repository. So maybe you might want to know a description, a summary, a title. And so you can kind of click these buttons here and it creates these AI generated summaries to sort of minimize the amount of time the curators spend on trying to align the data and kind of allow them to focus more on the actual science itself. And then we've implemented a console at the bottom that can give you the actual sources. So if, for example, you don't know what assay was used for this particular experiment, and maybe this like magic wand can't figure it out, well, then you can kind of use the console and use natural language to ask about these documents. And then it can point you to the actual sources. We can find more information and then fill it out yourself. And the idea is that once you're done and once you've curated this data set, you can kind of download it and then, you know, import it into your repository, and it should be easier to do. And then here on the left-hand side, you can create collections for the different types of studies. So all this is based on RAG, retrieval augmented generation. And so it creates these vector databases that allow us to sort of search through our repository. But yeah, and so kind of this is sort of the whole picture. You know, we have all these different data that might be structured, unstructured, semi-structured. And so RAG allow us to kind of create these summaries for future discoverability. So we're a big team of curators, scientists, software engineers. So yeah, Hopefully that made a little sense. And if you have any questions, always feel free to reach out. Thank you.
So, hello everyone. So thank you for staying to last talk. So I'm Sushma Naithani. I'm an associate research professor at Oregon State University and lead biocurator for plant reactome database. So today I'm going to, I think I have presented plant reactome talk last year also, so I'm just going to have a brief introduction for some of you who are new. So plant reactome database is the secondary pathway, a secondary knowledge base. So we use a lot of information from the primary data sources and integrate that and construct a knowledge about biological processes and pathways using reactome data model. And so, yeah. And so here we use the rice as a reference pathways for curating manually the rice reference pathways, and then we use gene orthology based projections to the another 130 species or more. And this is how we have the curated pathways and projected pathways that are hosted in the knowledge base. First time plant reactome was funded in 2012, and we started with the metabolic pathways, hormone signaling pathways. And as we moved further, we started including different type of the biological processes that are illustrated now in form of pathway using our data models. So some of the newer one are biotic and abiotic stress pathways depicting plant tissue, cell, and organ developmental pathways, gene regulatory networks, and more recently with the NASA funding, we have created the gravitropism pathways. We are free and open access pathway, and here one can look into the more recently published paper that describes our resource and tools in detail. Again, we link to various entities that are present in the plant reactome pathways with other pathway with other public resources, like for proteins with UniProt or for metabolites with the NCBI, PubChem or CAVI. So we are kind of one of the platform where one can integrate data from many sources. So we can have like gene protein and other gene products IDs. We can integrate and show the gene expression profile. We can link to the metabolites and so on. So we exist in the ecosystem of the public databases and link to them whenever possible. So this is the current site of plant reactome database, and so I'm just showing you, we are very much ready to release the new release of plant reactome this week. I was hoping it will be done by today, but somehow not today. So this is the new updates for the pathways. Right now we have rice, and then we have 138 new species for which the projected pathways are available. And in the website, then one can also do the pathway browsing. We have integrated search, so one can search for the genes, proteins, metabolites, pathways, and so on. And one can also find our documentation here and contact information, tool information, and other information related to the database. So simply one can browse, and we organize our data in Neo4j platform, and that we just heard in a talk in the previous talk. And so it is very interesting pathway model to organize data, and especially for the search of the data is very efficient. So we like Neo4j, and as one can see, primarily we have a lot of curation of metabolic pathways, but now our challenge is that also to curate the biological process and connect those back to the metabolism. So we have few pathways in the stress response, we have some in the plant development, we have some of in the circadian and then cellular processes and so on. And accordingly, we are also organized these pathways on the left-hand side panel. And all these pathways that are new in this series, and one can see a lot of those are related to the gravitropism related pathways. And then we have also extensively updated some of the pathways where we can link metabolism with some of these processes. So by default, we show the reference pathways, but one can, so here are the pathways, and I'm showing you one of the example how we link different type of pathways. So for example, this is one of the newly curated pathways that is the strigolectone signaling, and it plays a role in gravitropism. And so here is kind of the signaling that is happening with the gravity signaling, and it is connected to the strigolectone biosynthesis, which is a metabolic pathway. And then this is the next pathway here, how it is leading to the cell differentiation and playing a role in axillary bird dormancy in the shoot. So then one can, click on this pathway, the first one, and one can go to the metabolic pathway or in the downstream, and one can see the next pathway. So this is kind of very easy to move also from one pathway to another pathway, and more of our efforts will be integrating and connecting metabolism to growth processes and stress response. Again, one can see the pathways by default in Oryza sativa, that is our species, but then one can have this pull down list, and there are about 138 other species for which one can look into pathways. So here is example from Arabidopsis thaliana, and we also use the EBI gene expression data that can be pulled into plant reactome. As one can see in the bottom panel, one can select any gene here or the protein product here, and can display the basal gene expression data for that particular thing. We have also tools. So our tools can allow us to compare reference pathways that are manually curated with any of the projected pathways, and one can also see how much conserved they are across dicots and monocots. So here is example rice versus maize, and then rice versus Arabidopsis, and this is one of the transcription network that we have curated associated with the gravitropism. One can also upload gene expression data, transcriptome data, proteome data, or metabolome data, and can do pathway enrichment analysis. And one can also download this data in the form of a table. So here I'm going to cover a few new things that we are doing with plant reactome. So as we have talked about that there is a journal lacuna or lack of gene annotation, and so even in the best of the best plant model, that is Arabidopsis, we have very small amount of genes that have the functional verified, and so 30% of genes have molecular function that has experimental evidence linked to it. Close to 39% genes or 40% genes have unknown function, and 30% have only one gene ontology term associated with them. So this is after 25 years in Arabidopsis. If we go to the maize or rice, then we have less than 10% genes that have experimental evidence for them, and more than 50% genes have unknown function. So there is huge need for the creating those gold standards and doing some of the biocuration and improving the gene functional annotation. There are two gaps. One gap, of course, there is not enough experimental data for all the genes. But the second gap is that there is a lot of published papers which are not linked to our databases and have not been used for associating that evidence to the gene function. And this is where we think that some of the manual biocuration and some of the AI-driven or text mining can support that. So this is one of the goals we hope. And so one thing is that looking into the experimental evidence, so we have used a lot of rice papers and rice data. we also did use the Arabidopsis data. But now we are also looking into the other crops and other species where we have functional information available. And so one of the example here, for example, a study in the barley identified a gravitropic gene, and this gene, as we can say, it is named EGT2 in barley, but in Arabidopsis it is identified as a transcription factor, and in rice it is currently annotated as an unknown function, gene with unknown function. And so we looked into, and so there is a very small one-pager publication in the Microplanty journal, and somebody knocked out this gene, which is related to barley EGT2, and they have almost the same phenotype at barley. So at least we think that this gene, if you knock out in barley or in Arabidopsis, typically the wild type roots are spread, but then if you knock out, then you have almost very, very vertical roots here. So you they become hyper gravitropic roots. And so we think, okay, based on these two information, one can annotate the rice gene. And now we can perhaps name the rice gene more because of the, I think, barley. We can have the functional annotation. It is a transcription factor, but also it is the transcription factor that is associated with root growth and angle formation. And then we can say it is also associated with the response to the gravitropism. So similarly, there was another gene which is discovered in barley, and again had the similar phenotype as EGT1, and it was named EGT. So that previous one was EGT2, and this is EGT1. And this has been only functionally characterized in barley, not in Arabidopsis, not in rice. And in Arabidopsis, it is named based on the functional domain, a TULIP2 gene. It is a part of a large gene family. And in rice, again, it has the Arabidopsis similar annotation as a TULIP protein, but then no functional association here. So we can use this barley information and project on both rice, and it can also get projected to Arabidopsis. And this is one way we think we can bring more functional evidence from another species. So we use the gene orthology all the time to predict the gene function. Similarly, we can have experimental studies in other systems and bring that as evidence. So using some of these information that we have captured from Arabidopsis data, from the rice data and barley, we were able to synthesize a pathway knowledge. So this is what we do. Second thing, what we are looking into, not only the papers, but publish peer-reviewed transcriptomic data, analyzing that genomic data. To synthesize the pathway and gene network. So we are reanalyzing and asking different questions from publicly available transcriptomic data, building the evidence for co-gene expression, as well as looking into promoter analysis and other type of data, and then building the pathway knowledge. Other thing, we are looking into how people can use this knowledge. So of course, researchers and people who are breeders, they can mine the knowledge, but there are other applications. And one example I show here, we have a collaboration with Seth Murray at Texas A&M, and we have published this paper. One can look for the detail, but basically one can look into plant reactome and any pathway knowledge base, and if we have pathways curated that are related to the disease response, one can look into which pathways, which metabolites, which genes are expressing low or high or changing, and then one can see what is happening in the living system, and if one can monitor those compounds. So see, here are some of the compounds that we have picked, and then perhaps one can go and develop some of the methods for remote sensing and use this knowledge for monitoring the disease spread or similar things in the landscapes and in the crop field. We also integrate plant reactome widget in Grameen and also with the NASA Gene Lab. So other communities they can access, and they can access the plant reactome data also in the PubChem, EVI Expression Atlas, and many other places. We are looking into the AI, more into the text mining, but also for the purpose of the omic data analysis, of course, putting the human in the loop. Similar strategies that some of you have described. And then I like to thank a lot of our undergraduate curators. So to date, we had 28 undergraduate students who have contributed to reading papers and building the gene summaries and doing some of the pathway curation. And I like to acknowledge past funding from NSF, USDA, DARPA, and NASA, and also our planetary team at OSU, as well as our collaborators, which are Grameen at Cold Spring Harbor, and Human Reactome folks at NYU and OICR, and then, of course, the SETS group with our recent experimentation and other communities that we interact, GLab, EABL, Agbiodata, and ISP. Thank you.
About the break. Okay, then if you have any question, then you can also ask during the break, sorry.